We've got a measure of the central location, the mean or the median. It gives us a feel of, on average, where the central location of the data is. But what about the spread of the individual observations? It's quite interesting to know how variable the individual observations are about that mean or median. And the usual way to summarise that is by something called the standard deviation, which is often abbreviated as SD. So the standard deviation can be thought of the expected difference between an individual value and the mean. So for this red blood cell data, then the mean was 8.03, but of course the individual values usually kind of differ from that, and the standard deviation is a measure of how different. So this formulae can be used to calculate it, and it needs to be based on the differences of each of the data values squared, because otherwise we'd be dealing with negative values and it's no good summing those up. So we sum the differences from the mean squared, divide by n-1 and take the square root, and that gives us the standard deviation. So if we do that for this data, we get 1.58 if you just put it into that formulae. And often you can get a package to do it. Excel will do it very easily. So that's saying that each of these individual observations differs by 1.58 from the overall mean value. You've probably come across something called the variance as well, so I've just sort of added in here that the standard deviation is related to the variance. It's simply the square root of the variance. So the variance is this part in here, the sum of these squared differences divided by n-1. But the standard deviation gives you a more interpretable statistic. It actually means something. The square of that value of a variance wouldn't be very meaningful. And so this is most appropriate for summarising the spread of a data if you've got a reasonably symmetrical distribution. You can imagine if this distribution was really odd and had outlying values right out here, then the standard deviation would be very influenced by it and would, be probably a lot larger than 1.58, but it wouldn't really be summarising the expected difference from the mean for the majority of the data. Yeah, if you do have a very skewed, really skewed or odd distribution, you might then think, well, perhaps the mean and standard error aren't the best way to summarise it. However, if you've got a large data set, then even if you do have quite a skewed distribution, it can still be appropriate to use the mean and the standard deviation. So that was looking at the spread of the data, how much individual observations vary about the mean. Probably the more important thing you want to do is say how accurate is that mean itself. And there's something else that another statistic related to the standard error that measures that, and that's called related to the standard deviation that measures that, and that's called the standard error, and often that's abbreviated to SE, or sometimes people put STD, ERR, but various abbreviations, but I think SE is probably the most common one. So that can be calculated quite easily from the standard deviation. It's simply the standard deviation, but it takes into account the sample size and by dividing by the square root of the sample size. So this is going to be the expected deviation if you were to take a new sample of the same size, how much you would expect that to deviate about the current mean. As you can see, it's dependent on the variation in the data, so the standard deviation, and also the size of the sample. So the larger sample gives you a lower standard error. The bigger your sample, then the more information you've got in the data, so the more accurate your mean is, the more conclusions you're likely to be able to draw from your analysis. So if we look at another measurement, platelets, which was taken in that study, and we'll just look at the 173 normal calves, and if we take the mean of platelets, we got just over 600. The standard deviation, about 230, so that's how much individual calves, the platelets of individual calves is varying or expected to vary about that mean, so quite a lot of variation. You'd expect maybe some values, of sort of 800, 900. And so this mean is very much a measure of central location. It's not the value that all your data are going to take by any means. But you want to know how accurate that mean is. or you might want to be more interested in how accurate the mean is rather than how variable the individual values are. So that's obtained by this standard deviation. So if we, standard error, sorry, and if we use this formulae here, we would divide by the square root of the sample size, which is 173, and we end up with 17.4, and that gives us the accuracy of the mean. So if we were to go out and do another study, similar calves, and take another 173 normal calves, we would expect the mean value to be, on average, to differ from roughly 602 by 17.4. So we'd expect the mean to be reasonably close to the one we obtained of roughly 602. So it's a really important part of summarising data, the standard error, and that's the statistic that gets used most in statistical tests to test whether means of two groups are actually different from each other. So that's just what I've said. If a second set of calves was observed, their mean is expected to deviate by 17.4 from 602. Of course, it won't do in every case, but that's what the expected difference is going to be. And yeah, I've just put a comment there saying in this case we've got a reasonably large sample. We've got 173, so it's led to quite a small standard error. If that sample, if we only had, say, 10 normal calves, we'd be looking at the square root of 10 here, and this standard error would be much larger, so we'd be much less certain about the location of the mean. So yes, standard errors are a key way of measuring the accuracy of the mean. Related to standard errors are something called confidence intervals. And I'm just going to talk about what are 95% confidence intervals, because they're the ones that are in most cases used. And a 95% confidence interval can be defined as the range within which a mean of a new sample would lie 95% of the time. So if you take a new mean with the same number of data points, it would give you a range within which you are more or less certain that the new mean value would lie. And it's calculated using a simple formulae from the mean and the standard error. And I'll mention in a minute where this 1.96 comes in, but it's basically the mean value plus or minus 1.96 multiplied by the standard error. So if we do that for the 173 normal calves, and for platelets again, we've got 601.6 as the mean, we had 17.4 as the standard error. We plug that into this formulae to get our 95% confidence interval, and we come out with about 567 as a lower limit and 635 as an upper limit. So this range, if we were to take another mean of calves, we would be fairly certain it would lie within this range. Only 5% of the time would the value that we observe lie outside that range. So this is another popular way that people find quite intuitive to summarise the accuracy of means. So it's got this value of 1.96 in, so where does that come from? You don't really need to understand this, but if you want to, it comes from something called the normal distribution. And the normal distribution is something that the mean is expected to follow. So this would be a histogram of means. If you took lots of means of the same sample size, this is the distribution you would expect it to have. Of course, it won't have an exactly normal distribution, but you can make the assumption that it'll be roughly normal. And the larger the sample size, then the more normal the distribution will become. And we've got quite a large sample here, so it's reasonable to assume a normal distribution. And the 1.96 comes in because it defines the area within which 95% of the data are expected to lie. So if you look at that area there, that's 95% of the total area under the curve, and the bits in either tail are going to sum up to 5%. What might happen if you take your new sample, you might have a value out here, but it's very unlikely. So most of the values are assumed to be within this interval, which is the 95% confidence interval. So it's quite a nice way to summarise the accuracy of your mean. However, having just sort of said, yes, you always use 1.96, I think I probably ought to add that occasionally people use t-statistics instead of 1.96, particularly with small small sample sizes, because the distribution, this normal distribution, it tends to have a slightly different distribution which is a bit wider, and that's shown in this diagram here, where the tallest, I think it's blue, the tallest blue line curve is the normal distribution, but there's a couple of smaller sample sizes. I think with the purple one we've got an n of 17, and then the red one an n of 5, and it's showing the expected distribution for smaller sample sizes, which then is called a t-distribution. And there are a set of values relating to t-distributions which would be substituted instead of 1.96. So don't worry about this if this is all getting a bit sort of garbled, normal distributions and t-distributions. It's just if you see somebody using a different value, so 1.96, or a package might use a different value to 1.96, there is a reason for it. If you're calculating by hand, I think people often just go with the 1.96, regardless of the sample size, but it's just to make you aware there are slightly more accurate ways of calculating confidence interval, particularly for smaller sample sizes. If you're getting it out as part of doing an analysis, the statistical package will probably use one of these t-statistics, which can be a bit different to 1.96 if you've got very small sample sizes.